Watch this video in Lesson Reach. Pause and ask questions, take a quiz, or get help with assignments. Link below.
What if I told you that for centuries, some of the world's most brilliant mathematicians firmly believed that negative numbers were just, well, completely fake?
Right, like they thought they were a glitch in the math or something?
Exactly, like an absurdity that didn't actually exist in the real world. And yet today, you can't even check your bank account after a busy weekend or look at a weather app in the dead of winter without interacting with them.
Yeah, it's wild.
We are entirely dependent on a mathematical concept that used to be considered completely impossible.
It really is a massive conceptual leap that we now just, take for granted. I mean, we interact with the symptoms of this math all the time.
The freezing cold wind on our face.
Right, or the empty wallet.
Yeah.
But we rarely look under the hood at the underlying code that makes tracking those things possible.
And that is exactly what we are decoding for you today in this deep dive. We have a fantastic foundational source for this. We are exploring section 3.2 of chapter 3 from Contemporary Mathematics.
It's a great section.
It really is. And to give this exploration some fun structure, we are taking on specific roles today. So I am officially stepping into the role of the student. I am here to learn to push back when things don't make sense and to try and wrap my head around the logic.
I love it.
And you, on the other hand, are the lecturer. You're going to guide both me and our listener through the mechanics of this material.
Well, I am honored to step into the lecturer role. My overarching goal today isn't just to, throw rules at you.
Right.
It is to completely demystify integers, explain the actual why behind positive and negative numbers, and demonstrate how this framework is arguably the most perfect tool we have for modeling complex real-world situations.
Wow, okay.
Yeah, we're going to look at how numbers behave when they're pushed and pulled in opposite directions.
All right, lecturer. My metaphorical notebook is officially open, but before we start applying this to my bank account or in complex data, we have to lay the absolute bedrock foundation.
Okay, let's do it.
What exactly is an integer? Because, if you pressed me for a strict dictionary definition right now, I would probably fail the pop quiz.
Well, the easiest way to grasp integers is to start with something you already know intuitively, right? Counting numbers.
Like 1, 2, 3.
Exactly. These are the numbers you naturally use when you're counting physical objects in a room. 1, 2, 3, 4, and so on.
Okay, tracking.
To build the family of integers, we simply extend that group. So we take all those counting numbers, we add 0 to the mix, and then we introduce all of their negative mirror images.
Oh, gotcha.
So -1, -2, -3.
So it's the whole numbers, 0, and the negative whole numbers.
That's it.
It seems simple enough, but the textbook spends a good amount of time pointing out what an integer isn't.
Yes, it does.
And I think that's where the definition really crystallizes for me. Because section 3.2 explicitly kicks out numbers like, say, 63.9.
Right, because decimals are fundamentally excluded.
Right.
An integer must represent a whole indivisible step. 63.9 is not a counting number, and it isn't the negative mirror of a counting number, so it doesn't make the cut.
What about fractions, then?
Fractions are also generally excluded. Take something like 2/7. If you try to divide 2 by 7, you end up stranded in the empty space between 0 and 1.
You aren't landing on a clean whole step.
Exactly.
Okay, let me put my student hat on and challenge that slightly, because this is where math can feel like a trick question to me.
Bring it on.
The textbook brings up the fraction 36/4. Now, that is visibly written as a fraction, right? It has a numerator and a denominator.
It does.
But 36 divided by 4 is 9, and 9 is a counting number.
Yes.
So is it an integer? Is this about the fundamental truth of the underlying value rather than, how the number is dressed up on the page?
That is the exact distinction to make. It is entirely about the final simplified destination of the value.
Oh, interesting.
Yeah, 36/4 is just the integer 9 written as a division problem. The same goes for square roots, by the way.
Right. The text mentions the square root of 24, which calculates out to roughly 4.899.
Yep, and because that lands on a messy decimal, it is not an integer. But the square root of 25 is exactly 5.
So that is an integer.
Exactly. It always comes down to the core value.
That makes perfect sense. It's about the destination. So speaking of destinations, how should I be visualizing this in my head as we move forward today?
The most powerful visualization tool is the number line.
Okay, the classic number line.
Right. Imagine a long, straight path. Right in the center of this path is your anchor point, 0.
Okay, I see it.
When you walk to the right, you are moving forward into positive territory. When you walk to the left from 0, you're moving backward into negative territory.
So 1, 2, 3 steps to the right, or -1, -2, -3 steps to the left.
You got it. And if you hold that image in your mind, you really unlock the secret of integers. They are communicating two critical dimensions of information simultaneously. First, they give you magnitude, which is the sheer size or distance from 0.
And second,
They give you direction. Positive means right, negative means left.
that dual nature, magnitude and direction, is exactly why this connects so seamlessly to the concept of net wealth, doesn't it?
That really does.
Which the textbook uses as its prime real-world example, because when you think about your finances, they essentially sit on a single continuous mathematical path.
That's a great way to put it.
Like your positive assets, right? The equity in a home or a savings account, those are steps to the right. They are pushing you forward.
But those positive forces are constantly interacting with the negative forces.
Unfortunately, yeah.
Right. Your mortgage, your car loan, credit card debt, these are forces actively pulling you to the left.
Yeah.
By expressing a debt as a negative integer, the math allows you to unify these completely opposing forces into one single system. You can treat money you have and money you owe using the exact same language.
It brings order to the financial chaos, honestly. But here is where my brain, and I suspect the brains of many people listening, starts to fight the math a little bit.
Oh, I know where you're going with this.
It's the cognitive trap of comparing the size of negative numbers. Section 3.2 issues a very clear warning about this.
The intuition really misfires here because we spend our whole childhoods learning that bigger digits mean a bigger number.
Exactly.
But the foundational rule for comparing integers relies entirely on that path visualization we just talked about.
Right.
The rule is simply this. Larger integers are always further to the right on the number line.
Right, but let me explain why that's hard to process initially for a lot of us.
Go for it.
Our brains are hardwired to see that the digit 6 is undeniably greater than the digit 2. I mean, 6 apples is more than 2 apples.
Of course.
So when you slap negative signs on them, the immediate instinctual assumption is that negative 6 must somehow be greater or more than negative 2.
Yeah, and to fix that misfire, you really have to temporarily ignore the absolute size of the digit and focus exclusively on the path.
Okay, walk me through that.
If you take 6 steps to the left of 0, you land at -6. If you take 2 steps to the left, you are at -2.
Okay.
When you look at those two positions, -2 is clearly further to the right. It is closer to the positive side.
Because negative 6 is way further left, it's like deeper in the hole.
Exactly.
So negative 6 is actually less than negative 2, even though the digit 6 is larger. The further left you go, the smaller the true value of the number becomes.
That is the fundamental shift in thinking, which naturally leads us to a concept that often frustrates students.
Absolute value.
You guessed it, absolute value. It is written as a number sandwiched between two vertical lines.
I remember those lines.
The absolute value is defined purely as a number's distance from 0, regardless of which direction it went.
And this is where I want to push back, lecturer, because as a student, I'm always looking for the practical application.
Fair enough.
I understand the path analogy. Whether I walk 30 steps left or 30 steps right, the distance covered is still 30 steps. My fitness tracker doesn't care about direction.
Right, it just logs the steps.
But in the real world of finance or data, when do I ever actually care about magnitude without direction? Like, why introduce absolute value into the conversation at all?
It is a vital question because absolute value bridges the gap between abstract math and physical reality.
How so?
Let's return to your bank account. The textbook uses the example of -435. The absolute value of -435 is just 435. You strip away the directional negative sign.
Okay, so the absolute value is just the positive version of the number.
Yes, but let's look at the why behind it.
Okay.
If you have a bank overdraft of -$435, the bank cares deeply about that negative sign.
Oh, they definitely do.
It tells them the direction of the money you owe them. However, when you open your physical wallet to pay that debt, you cannot hand a bank teller negative cash. You have to hand them 435 physical, tangible dollars. The direction is the bank's abstract concern, but the absolute value, the magnitude, represents the actual physical reality of what must leave your hands.
Oh, that is a fantastic way to look at it. The absolute value is the physical cash I need to clear the abstract math.
Exactly.
Okay, I am entirely sold on absolute value now. So we have magnitude, we have direction, we have our number line path.
Yep.
how do we actually combine these forces? Like, how do the mechanics of adding and subtracting work without just memorizing a textbook table?
The key is to think of addition and subtraction as combining forces or vectors rather than just doing arithmetic.
Okay, forces.
Let's look at adding two positives. It's incredibly straightforward. You take a step right, and you take another step right.
Yeah.
You're just moving further right.
Right. Positive plus a positive is a bigger positive. That's, kindergarten math.
Exactly.
Mm.
Now, consider adding two negative integers. You are combining two forces that are both pulling to the left. If you have a credit card debt and you add another purchase to it, you are just marching further and further left into the negative.
Debt piling on debt makes total sense.
Right.
But what about subtracting a negative? Because that phrase alone, subtracting a negative, sounds like a grammatical double negative that kind of breaks my brain.
It does trip people up. The rule is that subtracting a negative is the exact same thing as adding a positive. But let's figure out why.
Actually, let me try an analogy here to see if I am grasping the mechanics.
I'd love to hear it.
So, imagine I am flying in a hot air balloon. The balloon has an upward positive force, but it's tied down by heavy sandbags, which are a downward negative force.
Okay, tracking.
If I subtract a sandbag, if I remove a negative weight, the balloon instantly shoots upward. Taking away a negative force inherently creates a positive upward movement.
That is a brilliant visualization. By removing something pulling you down, you naturally go up.
So subtracting a negative is moving to the right on the number line.
Exactly. Now, the final scenario is adding integers with opposite signs, one positive force and one negative force.
This is where we look at which force is stronger, right?
You got it.
The textbook actually has a net worth example for this. Let's say a woman named Jennifer is owed $50 by one friend, but she owes $87 to another friend.
So we have a positive 50 pulling right and a negative 87 pulling left.
Right. And instead of doing the raw arithmetic, I'm just visualizing the forces. The absolute value of her debt, the 87, is physically larger than the absolute value of her asset, the 50.
Yes.
Because the downward negative force is stronger, her overall net worth has to end up in the negative. It's like taking 50 steps forward on the path only to have someone drag you 87 steps backward.
Yeah, you are going to end up in negative territory.
It's unavoidable.
And that intuitive understanding is exactly what the textbook aims for. It notes that internalizing this logic acts as a mental error check for your daily life.
An error check.
Yeah, like if you know your negative debts carry a heavier absolute value than your positive assets, and a calculator spits out a positive net worth, you don't even need to recheck the math to know you made a typo.
Oh, right, because you know the forces don't align.
Exactly.
It's an intuition check that prevents major financial mistakes. I love that. Now, adding and subtracting forces makes sense for basic transactions.
Sure.
But what happens when we need to scale things up? I mean, if I've been losing $15 a day for a year, I am not going to add negative 15 together 365 times.
Nobody has time for that.
Right. So how does the number line handle multiplication and division? The rules always felt a bit arbitrary to me in school.
They often feel arbitrary because they're taught as rote memorization rather than logic.
Yeah, exactly.
But the textbook boils it down to two outcomes.
Right.
First, if the two integers have opposite signs, one positive, one negative, the result is negative.
Okay, that one is easy to visualize. If you lose $10 in negative 3 separate times, you are scaling up a negative force. You are down $30.
Right. Scaling a negative keeps it negative.
I can definitely see that.
Now, the one that historically confused even the great mathematicians is the second rule.
It is.
If two integers have the same sign, the result is positive. We intuitively understand why a positive times a positive is positive.
Right.
But why does a negative times a negative equal a positive?
Yes, please explain the mechanism there, because two wrongs don't make a right in real life, so why do two negatives make a positive in math?
Okay, think about it through the lens of video playback. Let's say you film someone walking backward.
Okay.
Walking backward represents a negative direction on our number line. Now, what happens if you take that video and you play it in reverse?
Oh.
Playing it in reverse represents negative time.
Right, so if you play a video of someone walking backward in reverse, they look like they are walking forward.
Precisely. A negative direction multiplied by a negative flow of time yields a visually positive forward motion.
That is wild.
Right. The two negatives perfectly cancel each other's directional pull, resulting in a positive.
Wow.
So, same signs always yield a positive result. Opposite signs always yield a negative result.
That video rewind analogy completely unlocks it for me. It stops being a rule on a chalkboard and becomes like the physical logic.
I'm glad that helped.
So how do we synthesize all of this? Because Section 3.2 puts a massive emphasis on finding the mean or the average of a data set.
Finding the mean is the ultimate test of your integer intuition because it forces you to blend addition and division seamlessly.
Okay.
You calculate the sum of all your values, combining the positive and negative forces, and then you divide that total by the number of data points.
Let's look at the textbook's temperature examples to ground this.
Let's do it.
So we have the daily lows in Barrie, Ontario for a freezing week in February. The temperatures are all negative: -20, -12, -15, -23, -17, -13, -19.
Okay, when you add all those daily temperatures together, you are just piling negative forces on top of negative forces. You are marching way down the left side of the number line.
Right, and the total sum there is -119.
To find the average, you divide that negative sum by the 7 days of the week.
And based on our new logic, a negative total divided by a positive 7 days means opposite signs.
Exactly.
So the result must be negative. The average daily low was -17 degrees.
It's mathematically smooth.
It really is. But it gets far more interesting when the data is volatile. The text brings up Jada's checking account balance over a week.
Ah, yes. Jada's account is a perfect real-world stress test.
It really is.
She has mostly positive daily balances, right?
Yeah.
Like $1,250, $673, some days around $700.
Solid week.
But right in the middle of the week, she takes a massive hit. Her balance plummets to negative $1,500.
That is a terrifying Wednesday.
It really is. But banks often calculate your interest or fees based on your average daily balance over the month.
Oh, right.
So to find Jada's weekly average, we have to find the financial center of gravity for that highly volatile week. We sum up all the positive days, and then we add that massive negative 1,500.
We are throwing all those competing vectors into one pot. And looking at the numbers, the combined weight of her 6 positive days is ultimately stronger than the downward pull of that one terrible negative day.
Yes.
The absolute value of her combined assets overcomes the absolute value of that singular massive debt.
That's exactly how to frame it. The sum of all 7 days ends up being a positive 3,703.
Okay.
We take that positive sum, divide it by the positive 7 days, and we find that her average daily balance is roughly a positive $529.
The math acts as a shock absorber. It takes wild swings in positive and negative directions and finds the absolute truth of where you stand.
It really does.
I really love how practical that is.
And its practicality extends far beyond just money or weather, which leads us to the final portion of our deep dive.
Okay, what's next?
The textbook features a specific exercise 41, that applies integers to complex social systems.
I am ready for the final exam. Bring on the stress test.
Well, before we dive into the data, Section 3.2 uses a word problem involving a politician and single-issue voters. And just a quick clear note for you listening, we do not care about the politics here today. We are strictly crunching the mathematical data provided in the textbook.
Exactly. No politics, just vectors. We're looking at this entirely neutrally to see how integers track human behavior. So what's the setup?
A politician takes public stances on 3 separate issues and tracks how many voters they gain or lose based on each stance.
Okay.
For issue 1, they gain 127 voters but lose 154. For issue 2, they gain 350 but lose 83.
Got it.
For issue 3, they gain 306 but lose 158. The ultimate question is, after taking all 3 stances, what is the politician's total net change in voters?
Okay, let's process this without getting bogged down in tedious arithmetic.
Let's do it.
Let's look at the push and pull. On issue 1, they gain 127 but lose 154. Immediately, I can see the absolute value of the losses is heavier than the gains.
Yep, the negative force wins.
So issue 1 puts them in the red. It's a net loss of 27 voters.
Perfect. You identified the dominant force, now apply that to the other 2.
On issue 2, the gains are huge, 350, and the losses are small, just 83. The positive force easily dominates, resulting in a strong net gain of 267.
Right.
Issue 3 is a similar story. Gaining 306, losing 158. The positive absolute value is heavier, giving a net gain of 148 voters.
So we have a small net loss and 2 strong net gains. What is the final step?
We combine all 3 net forces into one final calculation. We add the negative 27, the positive 267, and the positive 148.
And the result?
The combined upward force of the 2 positive issues vastly outweighs the small downward pull of the first issue. The final result is a net positive integer of 388 voters.
You absolutely nailed the logic.
Thank you.
What makes this exercise so compelling is that it proves integers aren't just a language for banking or thermometers.
Right.
They provide a vital framework for tracking competing forces in almost any scenario in human life.
That makes total sense.
Anytime there are gains and losses, action and reaction, or push and pull, integers allow us to balance those scales accurately and find the objective truth of the situation.
Well, lecturer, I have to thank you. As the student today, I've gained a much richer appreciation for this.
I'm so glad.
To quickly recap for you listening, we've explored how integers give us this incredibly elegant, unified language. They allow us to process magnitude and direction simultaneously.
Yes, they do.
Whether we are dealing with positive wealth and negative debt, or gaining supporters and losing supporters, the exact same mathematical processes apply. It brings total order to the chaos of competing real-world forces.
It provides a reliable path to walk on, regardless of which direction the world is pulling you.
It really does.
Yep.
But before we wrap up today, all this talk about applying negative integers to the physical world has me thinking about something that wasn't covered in the textbook, but feels like the natural next step.
Oh.
Yeah. I want to leave you with a final, slightly provocative thought to ponder.
The student is turning into the philosopher. Let's hear it.
We have spent this whole time seeing how beautifully integers calculate negative values for net worth or temperature or voter turnout.
Right.
But what happens when we try to apply negative integers to dimensions of reality we traditionally view as strictly positive?
What do you mean?
What about physical distance in the universe? Like, can there fundamentally be a negative distance between two stars?
Oh, wow.
Or what about the passage of time itself? Can we mathematically have negative time? Does this elegant framework of integers suddenly break down when it hits the hard laws of physics? Or does our understanding of reality just need to catch up to what the math has been telling us all along?
That is a phenomenal question. Does the number line extend backward past the Big Bang?
Exactly.
It truly makes you wonder if the universe is as flexible as the integers that describe it.
It is definitely something to mull over the next time you step outside and that weather app reads -15, or you see a minus sign next to your checking balance.
Definitely.
You aren't just looking at cold weather or a weekend of overspending, you are looking at one of the fundamental languages of the universe. Thank you so much for joining us for this deep dive.